Okay, so the last piece that I need to cover regarding Faraday's law is the direction. And to illustrate what I mean by that, I'm going to return to my solenoid and magnet demo. All right, here's my demo. Here I have the solenoid. It's connected to this ammeter, and I have a bar magnet made of a stack of disc magnets. And when I put the magnet in one end of the solenoid, you see that I get a current, and that was a positive current. And when I pull it out, I get a negative current. So when we talk about direction, the last thing that we need to understand is how can we predict whether this current is positive or negative? Here, I put in the other end of the magnet, and the current is negative as it enters, and then positive as it leaves. Flip the magnet around, positive when it enters, negative when it leaves. So how can we predict which way the current is going to go? All right, so here's the formula for Faraday's law again. This induced EMF is equal to the negative time derivative of the magnetic flux. And as far as direction is concerned, this minus sign is the key to the direction. So I'm going to illustrate the importance of this minus sign by using some examples. And I'm going to use the same examples that were in problem number 2 of today's handout, which was handout 22. Okay, so I'm going to start with B, the magnetic field coming out of the page and increasing. Now on the right-hand side here, we have the change in the magnetic flux. And if the magnetic field is changing, which it is because it's increasing, then there's going to be a change in the flux. The other thing that could change the flux is the angle between the magnetic field and the loop that we're using, the surface, or the area. So we're going to say that those two things are constant for the purpose of illustrating what happens to the flux when B changes, okay? So if B is increasing, I'm going to draw a sample vector here. I'm going to call this B. And remember that this is going out of the page. Even though I'm drawing it left to right, this vector is this vector out of the page. So this is B at some starting time, so I'll call it B naught. And then if it's increasing, then at some later time, I'll call it B1, the magnitude has increased. That's what we mean when we say that B is increasing. We mean the magnitude or the length of the vector is increasing. So what was the change between time 0 and time 1? Using vector addition, the change would be this vector. So this is my delta B. And delta B, so B naught plus delta B, remember vector addition is tip to tail, B naught plus delta B equals B1, okay? So delta B, the sign of delta B is going to tell us the sign of this time derivative. And why is that? So going back up here, I'm going to write this time derivative like this, where I mentioned A, the area is not changing, so I'm going to take out the area, and what I'm left with inside is dB dt. And this is the instantaneous change, but the average change, so on average, so the average change, I can replace my dB dt with delta B over delta t, okay? And delta t is always positive because we're always going to be talking about moving forward in time. We're not time traveling into the past in any of our problems, okay? Time always moves forward, so this delta t is always positive. Area is a positive number, so the sign of delta B is the only one that could be negative, right? And so it's the sign of delta B that gives us the sign of d phi dt. All right, so I squeeze that in right here. The sign of delta B gives the sign of d phi dt. And so here the sign of delta B is, well, out of the page, okay? That would be the direction. So I'm going to write d phi dt is out of the page. But looking back at our Faraday's law, the EMF is going to have a direction that is negative of this right-hand side. So it's going to be the opposite of the direction of d phi dt. So that means negative d phi dt is into the page. All right, and then the last step is we're going to use right-hand rule number 3, where I'm going to take my right hand, I'm going to point my thumb in the direction of the right-hand side here, negative d phi dt, which we just figured out is into the page. So I'm going to point my thumb into the page, and my fingers are going to curl in the direction of the induced electric field. So the induced electric field around this changing magnetic field is clockwise. And again, your book calls this a non-Coulomb electric field. Okay, so this is the direction that conventional current would be driven around the loop, because remember, conventional current is positive, and the electric field for a positive charge points in the same direction as the force on the positive charge. So the positive charge, the positive current, would be pushed around the loop in a counterclockwise direction if B is out of the page and increasing. Okay, let's repeat that process for B coming out of the page but decreasing. So if it's decreasing, then I might have something like B naught. This is out, remember, even though we're looking at it from the side. And then at some later time, B is going to be shorter if B is decreasing. So I've got B1. And so what vector do I need to add to this one to get this one? Well, I need to add a negative vector, like this. This is delta B. So vector addition, tip to tail, this plus this is equal to this, okay? Which is the same formula that we had before. B naught plus delta B equals B1, okay? So we're solving that via vector addition. B naught plus delta B is equal to B1. All right, so that means delta B is into the page, therefore d phi dt is in, which means that negative d phi dt is out. And so now I go over here, right hand rule number 3. I point my thumb in the direction of negative d phi dt. So I point my thumb out, and my fingers wrap counterclockwise now. And so you can see that in one case, if the magnetic field increases, I get a clockwise current. If it decreases, I get a counterclockwise current. All right, now let's do the next case, which is for the magnetic field pointing into the page and increasing. So now, if I have my initial magnetic field, I'm going to draw it pointing to the left now, because this is in, all right? If you like, I'm looking at it from the side the same way I was before, but now it's pointing in, so it's the opposite direction. And at some later time, I'm going to have B1, which is longer, because B is increasing, all right? And so delta B is this. So I should have moved this somewhere else. So this is in. So delta B is in. So that means d phi dt is in. So negative d phi dt is out. So I point my thumb out of the page. My fingers curl counterclockwise. All right. And if we compare that to the other case where B was increasing but going out, I got a current going this way, clockwise. But if B is going in and increasing, I get counterclockwise. Okay. And then the last example is B going in, but decreasing. Okay, so B naught going in, and it gets shorter. So what do I have to add to B naught to get to B1? I need to add this negative vector. Okay, so this is pointing, this vector, if in is on the left, out is on the right, then this vector is pointing out. So d phi dt is out. So the negative of that is in. So I point my right thumb into the page, and I curl my fingers around in the clockwise direction. All right, returning to my example here. Let's say I have a magnetic field that's pointing into the coil from the right. Remember, the convention is that the magnetic field lines point out of the north end and into the south end. I actually don't know which end of this magnet is north and which is south because it's not labeled. But if I have guessed correctly, then the north end is here. The magnetic field lines are pointing into the solenoid. And as I move the magnet into the solenoid from the right, the magnetic field and the magnetic flux inside the solenoid is increasing. And the reason it's increasing is because the magnetic field strength is increasing because the magnet is getting closer. So this would be like the case of having a magnetic field that's going into the page and increasing. And in that case, you see that we get a negative current. Okay. Now when I pull it out, now I have a magnetic field that's decreasing because this is getting farther away. And since it's decreasing, the flux is decreasing, so the EMF is going to be the opposite direction. So it's in, we get negative, and out, we get positive. Now if I flip the magnet around, so let's say the south end is going in, then that's, remember the field lines go into the south pole. So having the south end pointing into the solenoid is like having the magnetic field pointing out of the solenoid, right? So the field lines are pointing out. And so as I move closer, I've got a magnetic field that's out and getting stronger. And as I pull it away, I have a magnetic field that's out and getting weaker. And that's why I get opposite currents in this case. And these are opposite to the in and out cases as well. So just to recap that one more time, if the magnetic field is out and increasing, I got a electric field and an EMF going one way. If it's out and decreasing, it goes the opposite way. If it's in and increasing, it goes the opposite way as it did when it was out and increasing. And then if it's in and decreasing, then I get it in the opposite direction as it was when it was in and increasing, and opposite of out and decreasing. Okay, so either flipping the direction of B or flipping whether it's increasing or decreasing will cause the EMF to flip as well.